Hello, this video is a continuation of gas laws. We're going to talk about the combined gas law, the ideal gas law, and how it relates to stoichiometry.
So when we look at gas laws, they are relationships between pressure, temperature, volume, and amount of gas. So first we have the relationship between pressure and volume, and that relationship is called Boyle's law. And it basically states that pressure and volume are inversely proportional to each other. So if the pressure were to increase, the volume would decrease. And if the volume were to decrease, the pressure would increase. Now, if we look at a gas at two different pressures and volumes, we would have an equation like this. So we have P1 times V1 equals P2 times V2, where the P's are the pressures and the V's are the volumes. The ones here are for the initial pressure and volume, and the ones here, the twos here, are for the final pressure and volume. Okay, we talked about Gay-Lussac's law, which is the relationship between pressure and temperature. And pressure and temperature are directly proportional. So that means if the pressure were to go up, that would cause the temperature to go up. And vice versa, if the pressure were going down, the temperature would go down. And if we have an initial and a final set of information, we'd have a relationship like this for our Gay-Lussac's. So we've got P1 over T1 equals P2 over T2. Again, the P's meaning pressures, the T's meaning temperatures, and then those ones mean the initial pressure and temperature, and the twos meaning the final pressure and temperature. We talked about Charles' law, which is the relationship between temperature and volume. And temperature and volume are directly proportional. So if the temperature were to go up, that would cause the volume to go up. If the temperature were to go down, that would cause the volume to go down. And again, if we had two sets of data, initial and final volume and temperature values, we would have this as our equation. So V1 over T1 equals V2 over T2, where the V's equal volume, the T's equal temperature, and the ones are the initial volume and temperature values, and the twos are the final temperature and volume values. Now, if we were to take these relationships and combine them together, we're going to have what's called our combined gas law. And that's if we have pressure, volume, and temperature changes, and nothing is held constant other than the amount of gas that we have. So the relationship we have for the combined gas law would be P1 times V1 divided by T1 equals P2 times V2 over T2. Essentially, all we're doing is taking Boyle's law, Gay-Lussac's law, and Charles' law and combining them together. That's why we call it the combined gas law. Now, a couple of things about this relationship. Okay, first of all, the amount of gas doesn't change. Okay, so N is not part of this problem. And we need to remember that temperatures have to be on the absolute temperature scale. So your temperatures have to be in Kelvin. If they're given to you in Celsius, you have to add 273 before you can plug them into these equations that we've looked at. So now we're going to look at the same set of equations. So we've got Boyle's law here. We've got Charles' law here. We've got, Gay-Lussac's law here and Charles' law here. And now we're going to add in the relationship that involves the amount of gas. So this is Avogadro's law. And it's the relationship between the volume of the gas and how much gas we have. Remember that N stands for the number of moles of gas. And the number of moles of gas and volume are directly proportional. If we were to increase the number of moles of gas we have, that would increase the volume. If we were to decrease the amount of moles of gas, that would decrease the volume. And when we take these four relationships and put them together, we're going to end up with the relationship that involves pressure, volume, amount of gas, and temperature. And that's called our ideal gas law. where we're going to be using a proportionality constant R, which stands for our gas law constant. So if we rearrange this relationship a little bit, we get PV equals nRT, and this is our ideal gas law equation, where P is pressure, V is volume, N is the number of moles of gas, R is a gas law constant, and T is the temperature, and the temperature has to be in Kelvin in order for this relationship to work. When we talk about our R values, they're dependent on the units for pressure. So if our units for pressure are in atmospheres, ATM, then our R value is going to be 0.08206 liter atmosphere per mole Kelvin. And that's so that the units of atmospheres cancels out during the problem. If we were talking about pascals, and we're looking at cubic meters, we've got 8.314. And if we're dealing with joules per mole Kelvin, we would be using 8.314. Now, this unit here will come into play more in the next chapter. So let's look at a couple of examples that involve the combined gas law and the ideal gas law. So we have here, we've got some chlorine gas. And we want to find out what volume would this gas be if the volume is measured at 34 degrees Celsius and 2.45 ATM. So we're going to use our ideal gas law. Okay, if we look at the problem, we're given the volume, or no, we're given the amount of gas that we have. We're given the temperature and we're given the pressure. So we can calculate the volume by manipulating our ideal gas law. So we've got PV equals nRT. We're going to divide both sides by P so that we isolate V, or our volume. So volume is calculated by taking the number of moles of gas, which were given as 3.50. The R value, which has to match up with our units for pressure. Since the units for pressure are in ATM, we're going to use 0.0821. This is just rounded off from the slide before. So 0.0821 liter ATM per mole Kelvin. Our temperature is 34 degrees Celsius, but we're going to need to add 273 to that in order to get our temperature in the proper units. So that's going to give us 307 Kelvin. And we're going to divide that by the pressure exerted by the gas, which is 2.45 ATM. And if we look at the units, okay, we've got moles here and we've got moles here. Those are going to cancel out. We've got Kelvin here and Kelvin here. Those units are going to cancel out. We have ATM here and ATM here. Those would cancel out. That's why we had to use this particular R value. And the unit that does not cancel out are liters, and that's what we're looking for. We want to find the volume of this chlorine gas. So we would take 3.50 times 0.0821 times 307, divide that all by 2.45. Okay, if we look at the numbers, they all have 3 significant digits in them. So we've got 36.0 would be the volume of this chlorine gas at 34 degrees Celsius and 2.45 ATM. So now let's look at another question. It says a sample of argon gas collected at a pressure of 1.50 ATM and a temperature of 25 degrees Celsius is found to occupy a volume of 22.2 liters. How many moles of argon gas are in the sample? Okay, well, we're trying to find N. We know P and T and V. So this is an ideal gas law problem. We're just going to have to manipulate the PV equals nRT equation to solve for N. So we've got PV equals nRT. In order to isolate N, we're going to have to divide both sides by R and T. And that'll give us N equals PV over RT. So for pressure, we'll plug in 1.50 ATM. For our volume, we'll plug in 22.4 liters. For the R value, we want it to match up with the units for pressure, so we'll use 0.0821. And our temperature is given in Celsius, so we have to add 273 to get that to Kelvin, and that gives us 298. And again, if we look at the units, ATM cancels out, liters cancels out, Kelvin cancels out, and we're left essentially with 1 over moles. We've got a fraction in the denominator. We just take the reciprocal in the numerator, so we end up with moles as our units, and that's what we're trying to find. We have 1.50 times 22.2 divided by 0.0821 divided by 298. We've got 3 significant digits in our problem, so 1.36 moles of argon gas would be in this particular container at these conditions. Now, both of these problems are ideal gas law problems. And we know that for a couple of reasons. First of all, it talks about the amount of gas. In the first problem, it gives us the moles of gas. In the second problem, it asks us for the moles of gas. So PV equals nRT is the equation we would use. The second thing is that we're not given initial and final values in these questions. Okay, when we look at ideal gas law, we're only given one set of values. If we're given changes in pressure, temperature, and/or volume, then we're looking at either Boyle's law, Gay-Lussac's law, Charles' law, or our combined gas law problems. We have information about our gas. I need to move this out of the way. Give me a second here. Okay, so it says, it is desired to inflate a bag with a volume of 939 millimeters or milliliters by filling it with nitrogen gas at a pressure of 0.640 atm and a temperature of 300 Kelvin. How many grams of nitrogen gas do we need? Okay, so we're given a volume, and we're given a pressure, and we're given a temperature. So we can use the ideal gas law to calculate the number of moles of nitrogen gas. And if we know how many moles of nitrogen gas we have, and we know the formula for nitrogen gas, we can figure out how many grams we need. So we're going to take our ideal gas law, PV equals nRT. We're going to isolate N by dividing by R and T. So we can calculate the number of moles of gas by taking the pressure times the volume divided by our gas law constant and divided by our temperature. So when we look at the problem, our pressure is 0.640, so we'll put that in for P. Now the volume is in milliliters. We need it in liters in the problem. Okay, we want it to cancel out with the units we have for our R value, which is liters ATM per mole Kelvin. So we're going to have to take that 939 milliliters and divide it by 1,000. And that's where this 0.939 comes from. And then since our pressure is in ATM, we're going to use 0.0821 for our R value. We want to make sure all these units are consistent. And since our temperature is already in Kelvin this time, we can just plug that right in there. And when we look at the units, ATM cancels out. That's why we picked that R value. Liters cancels out. That's why we had to do that conversion. Kelvin cancels out. We're left with 1 over moles. So that's going to give us moles. We would take 0.640, multiply it by 0.939. Divide it by 0.0821, divide it by 300, and that gives us 2.44 times 10 to the minus 2 moles of nitrogen gas. But the question wanted to know how many grams. So we're just going to do a conversion. Okay, if we use the periodic table, we can figure out how many grams there are per mole. Nitrogen gas is diatomic, so we take that 14.01 and multiply it by 2. We're canceling out moles and going to grams. So we're going to take the number of moles and multiply it by 28.02. And that's going to tell us we need 0.684 grams of nitrogen gas in order to inflate this bag to 939 milliliters at 0.640 ATM and 300 Kelvin. All right, so let's look at this question. Okay, it says a helium balloon has a volume of 1.00 times 10 to the 6th liters at 22.5 degrees Celsius and 754 millimeters of mercury. What will be the volume of the balloon at 76 millimeters of mercury and 240 Kelvin? Now, if we look at this question, we're given an initial and a final temperature. That's going to affect our volume. And we're given an initial and a final pressure. That's also going to affect the volume. So since we have two variables that are changing, we're looking at a combined gas law problem. So our combined gas law equation is P1 V1 over T1 equals P2 V2 over T2. This time we want to find V2. We want to find out what the new volume is after we change the pressure and we change the temperature. So in order to isolate V2, we're going to have to multiply both sides by T2 and then divide both sides by P2, and that gives us our equation. So V2, the final volume, can be calculated by taking the initial pressure times the initial volume times the initial or the final temperature and divided by the final pressure and divided by the initial temperature. So we plug in our values here. Now, if we look at the units, we've got millimeters of mercury in the numerator and millimeters of mercury in the denominator for our pressure. So millimeters of mercury cancels out. We've got Kelvin in our numerator and we've got Kelvin in our denominator. So that cancels out. We're going to be left with liters at the end. So if we change the temperature and the pressure of that 1.00 times 10 to the 6th liter sample of helium, the volume is going to go to 8.05 times 10 to the 6th liters. So let's look at a second problem similar to this. Okay, it says, what volume is occupied by a 1.70 mole sample of xenon gas at 0 degrees Celsius and 1 ATM? Okay, so we can do this two different ways. Okay, we can identify it as an ideal gas law problem because we have N, we have T, and we have P. So we can solve for V. Okay, or what we could do is recognize that 0 Celsius is the same as 273 Kelvin. That's the absolute zero value, our standard temperature, not our absolute zero, it's our standard temperature. And 1 ATM is our standard pressure. So this is at STP. So maybe a little bit of an easier way to do this problem is to realize that because we're at STP, 22.4 liters will always equal 1 mole. Okay, if the temperature was not standard temperature or the pressure was not standard pressure, we couldn't do this. This relationship, this 22.4 liters equals 1 mole, is only at STP. So if we have 1.70 moles of xenon and we're at standard conditions, the volume is 38.1 liters. But again, you could do this problem a different way. Since you're given N and you're given T and you're given P, you could use the ideal gas law equation as well, and you would get exactly the same answer. So let's look at a couple of other types of gas law problems. This says a 15.5 gram sample of an unknown gas occupied a volume of 5.75 liters at 25 degrees Celsius and 1.08 ATM. Calculate the molar mass. So let's think about what we have here. Okay, we want to calculate the molar mass. Okay, well, we should remember that molar mass is grams per mole. Okay, so this is what we need to come up with, grams per mole, in order to figure out our molar mass. It actually gives us the grams. So it's giving us the numerator that we need in our problem. We need to calculate the moles. Well, we're given the volume, the temperature, and the pressure. So if we use the ideal gas law problem, we can calculate the moles, and then we can take the grams divided by the moles, and that'll give us our molar mass. So PV equals nRT. We'll solve for N, and then we'll plug in our values. So our pressure is 1.08 atm. Our volume is 5.75 liters. We'll use 0.0821 to be consistent with our pressure units. We'll change our temperature to Kelvin, and we'll be able to figure out how many moles of gas we have. So we have 0.254 moles of this unknown gas. But the question doesn't want to know how many moles of gas do we have. It wants to know what the molar mass is. So we're given the mass, 15.5 grams. We calculated the moles, 0.254 moles. We can figure out our molar mass. So we would take 15.5 grams, divide it by 0.254 moles, and that'll tell us our molar mass in terms of grams per mole. So the molar mass is 61.0 grams per mole. All right, so here's another question. Calculate the density of ozone. Okay, it gives us the molar mass is 48.0 grams per mole. And we're at 15 degrees Celsius and 1.75 atm of pressure. All right, well, we know what density is. Okay, density is an intensive property. Okay, that means it doesn't matter how much of it we have. So let's assume that we have 1 mole of ozone. It's a relative value, so it doesn't matter how much. So we're just going to assume 1 mole. And the reason we want to assume 1 mole is because then we know how many grams we're working with. Because 1 mole of ozone has 48.0 grams in it. All right, now we want to calculate the density. That means we need to know the mass and the volume. Well, if we're looking at 1 mole, we know what the mass is, 48.0 grams. So we know this number here. If we look at this part, if we have 1 mole of the gas and we know the temperature and the pressure, we can calculate the volume of that gas. And if we know the volume of that gas, we can plug it into our density equation and calculate our density. So we'll take our ideal gas law equation and solve for V. So we can calculate the volume by taking the number of moles of gas, multiplying it by R and T, and dividing it by P. Since we want the mass and the volume to be for the same quantity of gas, we're going to plug in 1.004 moles. We'll use our R value that's consistent with our pressure units, so 0.0821. We'll change our temperature from Celsius to Kelvin, and we've got 1.75 for our pressure. That gives us 13.5 liters for our gas. So 1 mole of ozone gas has a volume of 13.5 liters and a mass of 48.0 grams. So we can calculate the density for ozone gas at this temperature and pressure. 48.0 grams over 13.5 liters tells us the density is 3.56 grams per liter. So here's another problem. A sample of an unknown gas is found to have a density of 1.62 grams per liter, a pressure of 0.716 atm, and a temperature of 48 degrees Celsius. We want to calculate the molar mass. So again, we kind of want to think about what we're given in the question and then how we're going to figure out our answer. So it gives us the density. Well, what does that mean? Well, it means that if we have 1.62 grams of this gas, it will have a volume of 1.00 liters. That's the definition of density, how many grams there are per liter. We also know our ideal gas law equation, PV equals nRT, and that makes sense that we're going to be using that because we've got a pressure and a temperature there. And we want to calculate the molar mass, which means we need to know the mass and the moles. Well, we have the mass of our sample. We have the pressure, the temperature, and the volume of the gas. So we can calculate the number of moles of gas, and then we can take the grams divided by the moles, and that'll give us our molar mass. So we'll take our ideal gas law equation and we'll first use it to solve for the moles of gas that we have. So we've got a pressure of 0.716 atm, a volume of 1.00 liters. We'll use our R value that's consistent with our pressure unit. We'll change our temperature to Kelvin. So this sample of gas is 0.0272 moles. So that means the mass is 1.62 grams. The volume is 1.00 liters. And the number of moles of gas in that sample is 0.0272 moles. We can calculate the molar mass because we've got the mass and we've got the moles. So our molar mass is going to be 1.62 grams divided by 0.0272 moles. So the molar mass of this unknown gas is 59.6 grams per mole. Now we're going to add on things that we did in the last chapter in with our gas law unit here, because we can connect stoichiometry and gas laws. So let's look at a problem. It says, consider the following reaction, which is often used to generate small quantities of oxygen. Okay, so here's our reaction. We've got potassium chlorate. It's going to decompose into potassium chloride and oxygen gas. So we're going to suppose that we're going to heat up 0.0100 moles of potassium chlorate in a test tube. And we want to find out how many liters of oxygen gas can you produce at 298 Kelvin and 1.02 atm. Okay, well, let's look at the balanced equation for a minute. If we know the moles of potassium chlorate and we have the balanced equation, we can do our stoichiometry to figure out the moles of oxygen gas. And if we know the moles of the oxygen gas and the temperature and the pressure of that gas, we can use our ideal gas law equation and figure out the volume. So our first step we'll do is a stoichiometry problem. We've got 0.0100 moles of potassium chlorate. The balanced equation, which shouldn't say mole, that's a typo there. 2 moles of potassium chlorate are needed for every 3 moles of oxygen. So we are going to produce 0.0150 moles of oxygen. The question doesn't want to know how many moles of oxygen are we going to produce. It wants to know the volume. So we're going to take the temperature and the pressure and the number of moles of oxygen gas and our combined gas law, or sorry, our ideal gas law equation and figure out our volume. So we'll take PV equals nRT and we'll isolate volume. Okay, we'll plug in 0.0150 for our moles, 0.0821 liter atm per mole Kelvin for our R value, so it matches up with our pressure units, and 298 Kelvin for our temperature, divided by 1.02 atm, and that gives us the volume of the gas. So the second part of this problem is from this chapter, which is gas laws. The first part of this problem is from the last chapter, which is on stoichiometry. So we're just combining two types of chemistry problems into the same problem. All right, so here's another problem. Ammonium nitrate which is NH4NO3, is an explosive that undergoes this decomposition. So it gives us the balanced equation. We know we're going to be doing some kind of stoichiometry with that. So if 10.0 grams of ammonium nitrate explodes, how many liters of total gas are going to be generated at 0 degrees Celsius and 1 atm? All right, well, we have the grams of ammonium nitrate. We have the formula, so we can figure out the molar mass. We can convert grams of ammonium nitrate to moles. And in the balanced equation, it tells us for every 2 moles of ammonium nitrate that reacts, we're going to produce 4 moles of water vapor, 1 mole of oxygen gas, and 2 moles of nitrogen gas. That means total, we're going to produce 4 plus 1 plus 2. We're going to produce 7 moles of total gas. So we're going to do a conversion from grams to moles, and then we're going to do a mole ratio. We'll figure out the total moles of gas that's produced. And then we're going to take the total moles of gas and the temperature and the pressure and figure out the number of liters by using our ideal gas law equation. So 10 grams of ammonium nitrate, we look up the molar mass. So we've got nitrogen times 1 plus hydrogen times 4 plus nitrogen times 1 plus oxygen times 3. So that's where this 86.06 grams per mole comes from. This is the periodic table. Then the balanced equation tells us 2 moles of ammonium nitrate will produce 7 moles of total gas. And then we could use our ideal gas law equation, or because we've got 0 degrees Celsius and 1 atm, we're actually at standard temperature and pressure. We could just plug in that 22.4 liters equals 1 mole. Either way, calculate the moles of gas and use your ideal gas law, or use this 22.4 liters since you're at standard temperature and pressure, and you're going to get the volume. So the total volume of gas that's going to be produced is 9.90 liters. All right, another problem. When we look at the airbags that are in cars, they're filled with nitrogen gas by decomposing sodium azide. So here's our balanced equation. And if you see a balanced equation in a problem, you're probably going to need to use stoichiometry somewhere in the question. So in this case, it says how many grams of sodium azide are needed to generate 60.0 liters of nitrogen gas at 1 atm and 26 degrees Celsius. All right, well, 1 atm is standard pressure. 26 degrees Celsius is not standard temperature. So we're not going to be able to use 22.4 liters equals 1 mole in this particular question. So we're going to take the volume and the pressure and the temperature, use our ideal gas law to figure out the moles of nitrogen gas. And then once we know the moles of nitrogen gas, we're going to do our stoichiometry to figure out the moles and then the grams of the sodium azide. So let's look at the first part. We've got our PV equals nRT. Okay, here's our ideal gas law equation. We're going to solve for the number of moles of nitrogen gas by dividing by R and T. So we've got P times V over R times T. Okay, we're going to change our temperature to Kelvin so our units are consistent. We're going to get 2.44 moles of nitrogen gas. So now we know how many moles of nitrogen gas we have. We can use our stoichiometry to go from moles of nitrogen to moles of sodium azide. And then we want to go from moles of sodium azide to grams of sodium azide. So we're going to need to know the molar mass for NaN3. So 2.44 moles of nitrogen gas. The balanced equation tells us that 3 moles of nitrogen gas are produced for every 2 moles of sodium azide that is decomposed. And then the periodic table tells us that 1 mole of sodium azide equals 65.04 grams of sodium azide. So we would need 106 grams of sodium azide in order to produce this amount of gas.